Welcome to Mana Studies. Let's begin with 11th's first chapter, that is sets. So now what is a set? A set can be defined as the definition of set is a well-defined collection of objects. For example, the set of states, the set of Indian states. So this set will comprise of Maharashtra, Uttar Pradesh, Madhya Pradesh, and so on. But if I create a set of the following: Maharashtra, Delhi, Uttarakhand, now this will be incorrect. The reason being, the definition of set comprises of states, and in this collection Delhi is not a state, therefore making this an incorrect set. Now each element in this is the object of a set, or it can also be known as the member of a set. A set is like a family that share some common characteristics. Now those common characteristics should be well defined, and the members of the family are also known as elements or objects. Generally, the set is denoted by capital letter A, B, C, and so on. The members are generally denoted by lowercase. Now let's move forward to representation of sets. The most important thing about human civilization is communication. Now if I'm thinking of a set, then I should be able to communicate that message to the next person as well. So for that we need to write them down. So representation of sets, we have two different methods, which can be broadly classified into two different methods. One is the roster or tabular method. In this method, we are going to list all the elements. Let's take an example of first five even natural numbers. They will be 2, 4, 6, 8, 10. Now this is a well-defined set because we are considering even natural numbers and first 5 even natural numbers. 1, 2, 3, 4 and 5. Natural numbers are those which begin with 1 and go on till infinity, but we are only counting till 5. Now let's move forward to the second category, that is set builder method. In set builder method, we are going to mention the property by which we are going to classify the elements. Over here, as we can see, an example which states that x is a prime number less than 10. So now if we want to study this set, so first let's look at what are prime numbers. Prime numbers are those which are greater than 1 and have only one factor, that is themselves. So the possible prime factors are going to be 2, 3, now 4 won't be a prime number, 5, 6 won't be, 7, and so on. But it is only talking about prime numbers less than 10. So we won't go forward and we are going to close the set. Now this set will comprise of 2, 3, 5, 7. They all are prime numbers which are also less than 10. Hence, in set builder form, we can write this set in this manner. Now, it is written in this manner, thereby it is also known as the property method because we are explaining the property by which each and every member is different from those members which are not present in the group. Now, let's look at the another example, which is 2x. Now, because 2x becomes the member of this set, whereas the property remains the same. So now the elements are going to get doubled and this will become 4, 6, 10, 14. So now this set will comprise of the prime numbers less than 10, but the elements are going to get doubled. That is the reason why we had to double all the elements from the previous set. Okay, now let's look at another classification, that is an empty set, which is also known as null set or void set. If there is a set that contains no elements, then it is known as null set or an empty set. It is denoted by empty braces since it contains no elements, and it can also be denoted by the symbol phi, which is written as phi, phi. Now there's a common mispractice of writing this as an empty set. This is incorrect because if you write the symbol phi inside curly braces, now this becomes an element of the set, and since we are talking about empty set, so the set should not contain any element. So this is not empty because it contains an element, that is phi. Now let's look at the other topic, that is number of elements, which is also known as the cardinal number. Now how do you count the number of elements? It is going to follow natural numbers. If there is a set which contains 2, 3, 10, 14, so the number of elements would be counted as 1, 2, 3 and 4. That is, the sequence would be as per natural numbers. Now let's look at an equivalent set. If the two cardinal numbers, if two sets have the same cardinal numbers, then they are called as equivalent sets. For example, I have a set A. It contains 1, 2, 3. If I have another set B and that contains 11, 12, 13. Now the cardinal number of set A is 3 and the cardinal number of set B is also 3. Therefore, I can say that set A and B are equivalent sets. A and B are equivalent sets. Now let's look at another classification, that is a finite set. Now finite set are those which contain elements which are countable. Let's say it contains A, E, I, O, U. So it's a set of vowels. The set of vowels contains 5 elements. So the cardinal number of this set would be 5 and it's written as n. Let this be set A. So the number of elements in set A is equal to 5. And because the number of elements is countable, therefore it is going to be known as a finite set. Let's talk about another classification, that is an infinite set. Now if the elements of any set cannot be counted, then it is known as an infinite set. Let's take the example of natural numbers 1, 2, 3. They continuously go on. Let's talk about whole numbers. The set of whole numbers will contain 0, 1, 2 and so on. If we talk about integers, so now the set of integers will comprise of positive integers. It will also contain negative integers which cannot be counted. So they all will fall under the category of infinite sets since the number of elements cannot be counted. Let's look at another, that is identical or equal sets. If I say that there is a set, it has the elements 2, 4, and if I have another set, let's say B, which also contains the same elements 2 and 4, then the two sets are known as equal sets or identical sets. It's different from equivalent set because in equivalent set only the cardinal number of two sets is same. So in this case, even if the elements were different, still they would be equivalent. But for them to be equal sets, all the elements should necessarily be also the same. Now let's look at the other slide, that is a subset. Now what is a subset? A is called the subset of set B if all the elements of A are present in B. Let's take an example. There is a set A that contains 1, 2. There is another set B. It contains 1, 2 and 3. Now all the elements of A are in B. As the line goes, A is called a subset of B if all the elements of A are in B. Since all the elements of A are present in B, therefore we can say that A is a subset of B and it is denoted by this symbol. Because all the elements of A are present in B, it's called a subset. So now as we were focusing on this, if all the elements of A are present in B, then A is a subset of B and B is known as the superset of A. So A is a subset and B is known as a superset. So now let's move forward. And the next slide will be, okay, so now we are going to talk about a proper subset. A proper subset, A is the proper subset of B. Then all the elements of A are present in B and B should have at least one extra element. Let's say A comprises of 10, 12, 14. For A to be a proper subset of B, we can say that only if B contains all these elements and at least one extra element. If it contains at least one extra element, then we can say that A is a proper subset of B because all the elements of B are present in, all the elements of A are present in B along with an extra element. If the number of, let's solve a question. If the number of elements in A is m, then we have to find the number of subsets of A. So before solving this, let's look at a particular example. Let's say A contains two elements, 1 and 2. Now we are going to write down all the possible subsets. One possible subset of A is going to be a null set. That is an empty set because empty set is going to be present in all the sets. Another possible subset could be 1, 2. That is the sets containing exactly one element. Now there is also a possibility that both these are present. Now, this won't be a proper subset, but it will still be a subset because all the elements in this are also present in this. So we can say that a set containing all these as elements will be the proper subset. So as we can see, the subsets of the set A are going to be these. So the number of subsets in this case is going to be 4. A common observation will be when the cardinal number was 2, the number of subsets became 4. It can be written as 2 squared. Let's look at another example. Let's say a set B contains 3 elements 1, 2, 3. Now the subsets of these can be an empty set. Obviously it's a subset of all the sets. Now the sets containing exactly one element, either 1 or 2 or 3. Now sets containing exactly two elements, they could be 1 comma 2 or 1 comma 3 or 2 comma 3. Now a set containing all 1 2 3. Now this set will be a subset of this because all the elements present over here are also present over here. This won't be a proper subset, but it will still be a subset. Now all these elements, let's count them: 1 2 3 4 5 6 7 and 8. So the number of subsets of B of set B are equal to 8. This can be written as 2 to the power 3. Over here the cardinal number was 3. So the general formula can be written as the number of subsets for any set which has m elements can be written as 2 to the power m. So if a set A has the number of elements as m, then we can say that the number of subsets will be equal to 2 to the power m. Now let's have a look at an example which is saying that A has two elements 1 and 2, B has three elements 1, 2 and 3. Then we can say that A is a subset of B because all the elements in A are present in B. A is a proper subset because B has at least one element that is not present in A, and obviously A is not equal to B because of this extra element, and that is why it's a proper subset. Let's look at another example which states that A has two elements 1 and 2, B also has the same elements 1 and 2. Now A is a subset of B. All the elements in A are present in B. A is not a proper subset because B has no extra element. That is the reason why it is not a proper subset. And since it is not a proper subset, A is the subset of B, and also B is a subset of A because the reverse is also true. That is why we can say that A is equal to B. Let's have a look. Null set is the subset of each set. This is the observation which we made in the previous slide, because if I take any set, let's say P, it contains three elements A, B and C. Now we can say that null set is the subset of this set. If I say Q is a null set, then all the elements in Q are present in P. That is the reason why we can write Q is a subset of the set P. Each set is a subset of itself because all the elements of P are also present in P. So we can say that P is a subset of P. Now let's look at another topic, that is intervals. Now let's look at another topic, that is intervals. Intervals are the subsets of real sets. To understand the concept, let's take into consideration a number line. A number line is a one-dimensional representation of all the numbers. So now let's start from 0. If I say that I have to take all the numbers between 0 and 1, then I'm going to take from here to here. When I'm saying between 0 and 1, we are not going to include 0 and 1 because the word between means the numbers that are coming in between the two marks. So it's going to be a subset of the real set. The real set contains all the numbers. It contains all the numbers, whereas the set which I am considering, let's call it A. Now A contains numbers between 0 and 1. Now in order to write them mathematically, we are going to use some notations. Now there are different notations. These are known as square brackets. which denote closed interval. Now the meaning of closed interval is that we are going to include the elements present at the extremes. If I'm writing A and B inside closed interval, inside square brackets, it means that on the number line, if I'm going to place A, if I'm going to place B, then the number A and the number B, they are going to get included in the set. Whereas if I write the parenthesis, that is open interval. In this case, if I'm writing the numbers as C, D, then on the number line, the numbers between C and D will be included, and the numbers C and at D will not be included. They are going to be excluded. Now there is a possibility of another combination as well. That is, let me go back. Yep. Now the other combination is a square bracket and a closed bracket. Let's say E and F. So now this on the number line would be represented as E will be included, and F, because it's open bracket, F won't be included. If E is included and F is not included, then the set will comprise of E and the numbers between E and F. It will constitute of E and numbers between E and F. Needless to say, when I'm saying between, the number E and the number F are not included, and that is why we have to write E separately, because as the square brackets indicate that E will be included in this set. Now let's look at another possibility, that is an open bracket and then a closed bracket. Let's say the variables are G and H. Now on the number line they will be represented in a bit different, in a different manner. Let's say this is G and this becomes H. G is at open bracket, so G won't be included, but because H has a square bracket, so H is going to be included. Now the set will contain all the elements between G and H. Along with that, it will also include the element H. When I'm saying between means that between G and H without G and H. So we have to separately write the element H. Now let's look at the other slide, which says a power set. Now a power set is a set of all the subsets of a particular set. Let's say there is a set 1, 2. How many subsets can be created? As the formula which we have studied, there are going to be 4 subsets. Now what are the possible subsets? Either an empty set or 1 or 2. Now these are the sets which contain exactly one element. There is another possibility of creating a set that contains exactly 2 elements. Since there can be 4 subsets, so the power set is going to contain all of them. Hence the cardinal number of the power set will be written as 4. Now let's write what the power set would look like. The power set of the set A would include all these but as elements. Now over here they are sets. But when I'm going to write the power set, then each set becomes an element of that power set. So we are going to write them as an empty set, set containing 1, set containing 2, set containing 1 and 2. So now this is the power set of A. It has 4 elements. Let's take that example again. If I say that A has 1, 2, then the power set of A will contain an empty set 1, set of 2, set of 1 and 2. Now if we have to figure out, then I'm going to write the empty set. Now this is an element, so it belongs to the power set. Now because this empty set, in this case it's not a set, it's an element. Therefore we can say that this belongs to the power set. But if I write it in this manner, now this is an element inside curly braces. So now this is a set which is a subset of the power set. Now these two indicate different meanings. Over here as we can see, the curly braces is an element. This is an element or a member. Because it's an element or a member, So we can say that it belongs to the power set. But when I'm putting this element inside curly braces, now it becomes a subset of the power set. The other topic is a universal set. Now, the set containing all possible elements in a given context. Because of the word context, the definition of universal set is going to continuously change as per question. If I'm talking about a set A that contains 1, 2, 3, and another set B that contains 4, 5 till let's say 100, then the universal set of these two will be the set of natural numbers. And if either one of them included a 0, then the set instead of natural would have become the set of whole numbers. Okay, now this is a Venn diagram. Venn diagram are visual means of representation of different sets. Now let's talk about operations on sets. The basic operation on a set is union. As we all know, the word union means being united or standing together. If we have two sets which are represented by the Venn diagram and the two sets are A and B, then the union is going to be the elements which are in A, which are in B, and they can also be present in both of them. So they can be represented as this diagram. Now the next topic is the operation on sets. The first of that will be union. Now union of two sets A and B is denoted by a capital letter which is similar to U. And it's a set which contains all the elements and those only which are either in set A or in set B or in both of them. So if I'm going to use a Venn diagram to represent this, that is A union B. It is going to contain those elements and those only which are either in A or in B or in both. So the shaded portion represents A union B. Now let's talk about the union law. But before that, let's see what does the word property even mean. Property is a characteristic that applies to a given set. If I'm saying commutative property, so let's take the example of addition. If I write 2 plus 3, it can be written as 3 plus 2. The two elements 2 and 3 can interchange places and still the answer remains the same. Therefore, it comes from the word commute. Commute means to travel from one place to another. And since I can say that A plus B is B plus A, the two elements can commute and interchange places. Therefore, the property is known as commutative. As we can see, A union B is the same as B union A. By the very definition, B union A would contain the elements and those only which are either in B or in A or in both. Hence, we can say that it is commutative. Now, let's look at associative. Associative means that the order in which a property is applied does not matter. Since we have 3, in case of numbers we were using BODMAS, but in this case let's see, if I am taking the union of B and C, then there will be a combined set of these two, then taking the union along with this would render the same result as taking the union of A and B, then taking the union with C. Therefore we can say that it is associative as well. Now, idempotent. Idempotent property is an interesting one. Let's say there is an element denoted by star. There is some operator in between, and there is the same entity as was in the first case. If the result is the same as that entity, then the property is said to be valid. If star operator star gives us the same thing, then we can say that the idempotent property holds true. As in this case, A union A. What will that be? Let's go by the definition again. A union A is a set which contains all the elements and those only either in A or in both. On the Venn diagram, it will be represented by all the elements inside the set A. So A union A can be written as A. And as we saw earlier, star, some operator, another, the same thing, star, will give us the same thing. Since A union A gives us the same thing, we can say that it is idempotent as well. Now let's look at the law of identity. It states that if I take the union of set A with the empty set, if I'm taking the union with an empty set, what will the elements be? Either in A or in empty set or in both. Since all the elements are present in A, it will be written as A. Let's look at the other part of it, that is A union a universal set. The definition of universal set keeps on changing as per context. In this case, the universal set will contain all the elements of the context by which A is defined. Now let's look at intersection. Intersection of two sets represents the common elements. If I have the Venn diagram which represents set A, set B, then all the elements falling in the common part will be written as A intersection B. Now let's look at the properties, but before that, another important topic is disjoint sets. If two sets don't share any elements, then they are said to be disjoint. Now commutative, as we earlier saw, if I change the places of B and A, still the result remains the same, so it is commutative. In the case of associative, if I take the common part of B and C before and then I take the common part with A, and on the other hand I take the common part of A and B and then I take the common part with C, still the result is going to be the same, so they are commutative, associative. Let's talk about the property idempotent. As we said, any entity or operator, the same entity should give us the same entity. Now in this case, if I have a set A intersection with A, now all the elements that are present in A which are common with A will be present in A. That is the reason why we can say that the property idempotent also holds. Now let's see the cases of the law of identity. A intersection phi. One set may contain finite or infinite elements, but the other set does not contain anything. Now what is the common element? The common element would be phi, or it can be written as empty braces. Now if I'm going to take the common part of a set A with the universal set, now how many elements would be common? All the elements of set A are going to be common as compared to the previous case. If I'm having a universal set and there is another set A, now I just have to pinpoint the elements that are common in both. They will be the elements inside the set A. Now it also has an additional property, that is distributive. If I write A intersection B union C, it can be written as A intersection B union. Now this will get distributed to both of them and we will write it as A intersection C. So the property of distribution also holds. The next topic is difference of two sets. Let's understand this with the help of a Venn diagram. If there is a set A, there is another set B. Now the difference of two sets would be the elements that are present in A and which are not present in B. For example, let's say that A contains 1, 2, B contains 1, 3, 4. So A minus B would contain the elements in A which are not present in B. 1 is present but 2 is not present, so it will constitute of 2. And B minus A would be all the elements that are present in B but are not present in A. This is A minus B and this is B minus A. Let's look at the next topic, that is symmetric difference. Now there are three different symbols, either delta or plus inside a circle or a minus inside a circle to denote symmetric difference. Now the symmetric difference is known as A minus B union B minus A. Let's look at the Venn diagram again. A minus B denotes all the elements that are in A which are not present in B. Elements present in A that are not present in B. That is A minus B. And over here we have B minus A. That is all the elements which are in B but not present in A. That is this. So now symmetric difference is denoted by the shaded portion. It can also be written as A union B minus A intersection B, because union is going to constitute everything and this is the intersection part that is going to get removed from the union one. Now let's talk about complement of a set. Let's look at the Venn diagram. If I have a set A that contains certain elements which is inside a universal set as per the context, now A will contain certain elements. Now A will contain certain elements and the elements which are not present in A, that is in universal set but not in A. Now they are denoted by a complement of set. It is written either as A bar or as A dash. From that we get De Morgan's law, which states that A union B dash is the same as A complement intersection B complement. So let's look at the Venn diagram. The another topic is De Morgan's law. As we can see, A union B complement is same as A complement intersection with B complement. Let's use Venn diagrams to look at this. If I write A union B, they can be denoted as the common part inside the two circles. But because it's the complement, so it will contain the elements that are not present in A and B. That is this shaded portion. Now let's look at the RHS. A complement. A complement will be denoted by the elements which are not present in A. B complement will be denoted by the elements which are not present in B. And if I'm going to take the intersection of these two, so it will be written as A complement intersection B complement, and the Venn diagram would be something like because we are going to take the common part from these two, so it will look like this. That is the same case over there. We are taking the common part. This is not common, this is not common. So eliminating them and only including the common part, we can say that A union B complement is the same as A complement intersection B complement. This can also be demonstrated by another example. Let's take this. A intersection B complement. This can be denoted as, inside a universal set, we have two sets A and B. The common part is excluded. So our set will contain of this shaded portion, and if I am writing A complement, that is the elements which are not present in A, and if I am writing B complement, that is the elements which are not present in B. And now we are going to take the union of these two. If I am taking union, union means either in one or in second or in both. So having a look at this, the union of these two would include everything except the common part. So this would look like the first case, as in this case we had A intersection B complement, and in this case we have A complement union B complement, and because they both are same, we can say that this is also proved. Let's look at another topic, that is number of elements for two sets. Let's explain that while using a Venn diagram. Let's say there are two sets A and B. I'm going to denote this region and only this, that is A minus B, by this symbol, denoting the region B minus A by this symbol, and denoting the region A intersection B by this symbol, and the remaining is denoted by this symbol. If I'm talking about the number of elements in these two sets, that is the number of elements in the set which is created by A union B. If I write number of elements in A, what are the regions which are getting included? 1 is getting included, 3 is getting included. So it will include 1, it will include 3. Now if I add the number of elements in B, now what are the elements that are being included? Region 3 and region 2. Now as we can see, I have taken 1, I have taken 2, but I have taken 3 two times. So I have to remove that, and I will write N A intersection B, that is region 3. So now I have 1, I have 2, and 1, 3 will get eliminated. So the formula becomes the number of elements in A union B can be written as number of elements in A plus number of elements in B, and we are going to remove the number of elements in A intersection B because they are coming two times, so we have to remove it once. Let's look at another example, that is for three sets. Again, let's take a simple Venn diagram which contains of three sets A, B, and C. I'll denote this region by 1, this region is denoted by 2, this region by 3, this region by 4, 5, 6, 7, and 8. Let's hope I haven't missed any. 1, 2, 3, 4, 5, 6, 7. I've included all of them. So if we have to calculate the number of elements that are going to be present in all of them, that will be denoted by A union B union C. If I have to include all of them, so the final result should include 1, 2, 3, 4, 5, 6, and 7. If all these have to be included, so the formula should be number of elements in A plus number of elements in B plus number of elements in C. If I'm going to add all the elements, the number to calculate the number of elements in A, B, and C, I will get 1, I will get 2, 3, 4, 5, 6, 7. But the thing to note over here is when I'm adding A and I'm adding B, for 3 sets, let's take the diagram A, B, and C. This is set A, this is set B, this is set B. To denote the regions, I'm going to take the symbols 1, 2, 3, 4, 5, 6, 7, and 8. If I have to take the sum of the number of elements in the 3 sets, what is the result that I want? I want 1, 2, 3, 4, 5, 6, and 7. In this case, if I'm going to add the first 3 sets, it will be NA plus NB plus NC. This is C. So now what are the elements that are being counted? 1, 2, 7, 6, 1, 2, 7, 6, 3, 2, 7, 4, 5, 6, 7, 4. It means I have counted 1, I have counted 3, and I have counted 5. These are coming one time each. But the regions 2, 4, and 6. Now the regions 2, 4, 6, they are getting included 2 times. Once 2 is included with A and once 2 is included with B. So they are going to get included 2 times. But in the case of the region 7, this is going to get included 3 times. So now what do I have to do? I have to remove 2, 4, 6 one time. So in order to remove 2, 4, 6, I have to write it as A intersection B, B intersection C minus A intersection C. If I'm removing these, what are the elements that are being removed? 2 will be removed, 7 will be removed, then 4 and 7 will be removed, then 6 and 7 will be removed. So I am including the regions 2, 4, and 6. They are being included one time. And 7, how many times will 7 be included? 3 times with each. So 7 will be included 3 times. So when I'm subtracting it, I am removing 2, 4, 6 one time. So in the final result, I will have 1, 3, 5. I will have 2, 4, 6, but 7 is completely removed. So I will have to add that region by writing it as A intersection B intersection C, and then 7 is included. So in the final result, this will cancel out this cancel out this. So I get 1, 3, 5, 2, 4, 6, and 7, which was to be proved.